Hello and welcome to another Stephen Mendes video. Thanks for watching. Here we have drawn some NOR gates and some NAND gates, and we have connected the outputs back to the inputs. And by doing this, we have created a feedback loop so that the output of one gate locks the behavior of the other gate, and we are going to get some rather predictable and interesting results from this configuration. The reason why we've joined them twice is because the outputs on the right-hand side can assume one of two possible stable states. We're going to show you that now. We can either have a 1, 0 or a 0, 1. Notice that for the NOR gates on the top, we have reversed the state, so we have the two possible states, one on the left and one on the right. And for the NAND gates below, we have done the same identical thing. So now all we really have to consider is the inputs. Let's see what happens with the inputs. Notice I've marked one of the inputs X. Why have I marked one of the inputs X? Because that input does not have the power to change the state. The particular input marked with an X has lost control of the flip-flop. It no longer has the ability at that point in time to effect a change in the state. However, the one marked 1 and the one marked 0 does have the capability to change the state. One last thing we have to do, and that is we have to label our outputs Q and Q bar. This makes sense because they're opposite. And we can say then that Q, when Q is a 1, the flip-flop is set, and when Q is a 0, the flip-flop is reset. Just like your rat trap, you can set it and you can reset it. Now, having labeled the output so that we have a specific output which we can designate as Q, and then obviously the other one will be Q bar, we need now to check what we're going to do with our inputs. Now, it turns out that the NOR gates respond to a 1 and the rest condition is 0, whereas the NAND gates respond to a 0 and the rest condition is 1. We can actually see that from our diagram because we have a 0 written in red on the input that's active. So the rest condition is a 0, and if we want to cause the animal or flip-flop to change its state, then we will cause a 1 to be put on that input, which will cause some action to occur, and the flip-flop will change state. Now notice I've written S and R for set and reset. And it is quite clear in the first flip-flop up on the left-hand corner that that is in the set condition. And when I put a 1 onto the reset line or the R line, it will change from being set to reset. And after it is changed, that reset line will lose control and not be able to cause it to change anymore. So a 1 on the reset line will cause it to change to the 1 on the right, and it will lose control. Then a 1 on the set line will cause it to change back from the right to the left. So I think you can get that, but in order to make it a little plainer, we're going to just concentrate on the one built with the NOR gates. And this time we've put all zeros on the input because we know that this one is triggered by applying a 1. So don't let the fact that we've put all zeros fool you, because we can have all zeros on the input and the flip-flop is perfectly comfortable in either the set or reset position as shown. So the two possible states are shown, one on the top with the set and one on the bottom with the reset. And we are going to now cause a change to happen very slowly. So watch carefully as we do this. We are going to cause the top 0 to become a 1. When we do that, clearly it has to go through the gate, and that 1 becomes a 0. Then we have two zeros on the bottom gate, which causes that 0 to become a 1. So what we've actually done is, by applying that 1 to the very top input, we have caused that flip-flop to change state. Now it matches what's on the bottom with a 0 on the top and a 1 on the bottom. So in other words, a 1 on the very top input line will cause the flip-flop to assume the state of in the bottom one. Now that 1 is not going to stay there. That 1 will eventually go back to a 0, and so actually the top diagram has turned into the bottom diagram. Let us now turn the bottom diagram into the top one. To do that, we make the bottom one go from a 0 to a 1, which changes its output from a 1 to a 0, which changes the input on the other one and causes that output to change from a 0 to a 1, which then causes the input on the other one to change from a 0 to a 1. Follow it slowly. If it's gone by too fast, rewind and play it in slow motion. Now what has happened is here, the 1 at the very bottom, after going to a 1, has gone back to a 0, and the pulse is passed. However, that very bottom line has lost control to cause any further change in the flip-flop. So the bottom flip-flop has now assumed the position of the top flip-flop at the beginning. Okay, so let us see what that means. If the input 1 that caused the flip-flop to change state now goes back to 0, the flip-flop holds its state, and this is the memory function of flip-flops. A temporary 1 or temporary pulse will cause the flip-flop to change its state, and it will hold its state until we get a reset, or if it was set, reset until we get a set. So watch in slow motion until you get it, and remember the NOR gate truth table as you trace your 1s and 0s through the device. Thanks for watching, and we'll see you in the next video.